券那个帽子拿回去了以后就给猫带过来，自己从来没带过。
给你家猫带。
给你家猫带过，给我家猫也带过。
Okay, let's go ahead and get started. Does anybody have questions before we get started? Okay, so this is where we left off last time. We were looking at Bayesian linear regression, and when we have multiple models to choose from, how do I choose the optimal model? And we talked about the evidence of models and maximizing the evidence. And so remember, this is basically the normalizing constant in the posterior. So it's just the probability of your data for that class of models. And so for the Bayesian, okay, 1 second. Go back. Bayesian linear regression, we had the polynomial problem where we had different models corresponding to the degrees of polynomial, and we ended up choosing, in this example, the third order polynomial, which turns out to be the right answer, but that doesn't always turn out that cleanly. But this was the evidence. And so that's where we ended, and I hadn't given you kind of what the evidence was in the Bayesian linear regression example. So I'm going to do that quickly first, and then we're going to talk about alternatives, ways to do model selection. So that's kind of the strategy for today's lecture. So I'm going to give a sketch of kind of the derivation of how you get this evidence function that I'm plotting. So you can see in the code, if you kind of look through it, the R code, what the formula is there that I use. I'm going to give you kind of how to, not step by step, every single bit of the derivation, just for the sake of time. I'm going to just give you the sketch of how to get there. So remember, the idea is that we have competing models, maybe M1 out to MK, and we want to maximize the evidence, which I was writing as the probability of your data given that model, M spy. So we want to find which model maximizes this one. And remember, again, this is kind of sort of wishy-washy notation because the MI is not really a random variable here. It's just a class of model like fifth order polynomials with the Gaussian prior on the beta coefficients that we talked about. So this is really not, be careful what this notation means. That's kind of the idea. Okay. But it is meaning that, you know, the P of Y that we have here really does depend on what set of rules we're considering. That's why we have this in the notation here. And of course, I'm leaving out a lot of notation. There's really like I'll put it here in a minute, but there's really like the X values in the regression. There's the sigma squared, which we were calling a constant. There's the lambda, which we call constant, all this kind of stuff. But for the time being, let's leave out the notation. So what is this value equal? Actually, let me do a job of, I'm going to run out of space if I start here. So we want P of Y given MI. This is just the, again, the denominator in the Bayes rule. And so we just have the integral of the thing in the numerator. The thing in the numerator of Bayes rule is the likelihood, the probability of our data given our beta coefficient, right? And now I'm going to put in the, there's the x values, and there's also our constant, and the sigma squared is also a constant we have in there. And then there's the P of beta, the prior of beta. And technically that also depends on the parameter lambda, right? And the normalizing constant is to just integrate this over beta. So again, the idea is that I want to know the probability of my data just given that I'm in this class of models, not depending on any particular choice of beta, so that I'm marginalizing out beta. Okay? Now, if I write all this out, and again, I'm going to kind of give you some of the steps, but maybe skip some steps just to save time here. This part's easy. This is just our Gaussian likelihood, right, for the y data from the regression model. And so we saw already this is like a product of n Gaussians, univariate Gaussians. I just get normalizing constant, this mutual thing, times a Gaussian, solve for norm y minus x beta squared, like so. So that's the likelihood term, right? This is just what we wrote down last time. And this guy, P beta, is also Gaussian. It's multivariate Gaussian with this lambda determinant 1/2, exponent minus 1/2 beta, lambda beta, like so. Okay, so that's just what we had written down last time anyway, right? This was just multiplying. This is basically the posterior that we were writing down before. We just never computed the normalizing constant for it. We just said that this is proportional to the posterior. Now we're actually going to compute the normalizing constant because I really do want to see the normalizing constant to understand what this evidence function is.
Now, where does n lie to be a factor? I don't see it when I look at myself.
Yeah, right. Yeah, good point. I really should have. There should be an mi in this notation, like here, and yeah, this should also have a kind of a given mi.
So is it the dimensionality of beta?
And yeah, and that basically mi is in our case, yeah. So this is now specifically to the polynomial case is first order polynomial, second order polynomial, kth order polynomial. I could have a zeroth order polynomial if you just have a mean and no regression line. And yeah, the I is going to be basically, the dimension is going to be I plus 1, yeah, of beta. So that's where that comes in. And we kind of loosen this notation because it's not really specified, but the mi basically makes this a I plus 1 by I plus 1 matrix and beta an I plus 1 vector. That's what changes. Yep, that's good. Okay, does everybody understand that? So yeah, so that's where the mi comes up. And so for each dimension, it also comes up, it changes the x, right? Because the x matrix can be put together as a column of ones, a column of just x, a column of x squared, and how many columns you have there is the order of the polynomial. It's going to be I plus 1 columns in x. So those are the things that change with the mi polynomial case. Yeah. In general, this might be just some linear regression model where maybe these aren't polynomial coefficients, they're just some covariates that you've got in your model, and maybe you've got some competing choices. We'll see an example that's not polynomial regression in just a minute when we get to the next topic, but this could be more general for the polynomial stuff we're talking about. Okay. So yeah, right, let's see. We already know that basically, I can pull these two normalizing these two constants out of the integrals, and then I can put together this piece and that piece inside the exponent. I'm not going to write that down. In the end, what you find is that you do the exact same thing we did last time, which was completing the square, remember, in terms of beta. You complete the square in terms of beta, and that gave us, we saw, I'm just going to write it as it was a normal distribution with mu sub n, or no, let me call it beta sub n posterior, and let me call it capital sigma sub n covariance. And so that was, remember, just we broke down kind of, we went through the derivation to get the posterior parameters for beta and its covariance. We saw that it was Gaussian. But when you complete the square, we, remember, had all those constants. We had like a quadratic term that let us read off the sigma. We had a linear term that let us then read off the mu or the beta in here. And then we ignored the constants that got left over from completing the square because they didn't help us decide what these were. But now it actually matters because I can't just throw away constants. They're going to change the value of the integral. So I'm going to keep these constants in here. So when I complete the square and pull together all the terms we had last time, this is the step I'm going to skip the details of. But when I pull together all those completing the square terms, what you find is that you have the constant terms left over look like the following. This is the completing the square terms that are left over from that. You get a norm y squared in there, and you get a plus 1/2 beta n transpose sigma n inverse beta n.
Now, we wouldn't really have to do that, right? Because we know what the normalization constant is for Gaussian, right?
No, the point is that when you put these two things together, they are not a Gaussian by themselves. If you normalize, so if you normalize this, then it would be a Gaussian. And the point is that we're going to have when you do the completing square, there's going to be these terms left over. Yeah. So we know the normalizing. The trick we're going to do is we know the normalizing constant here. And this is, by the way, this is a function of beta. So this is going to stay inside the integral of the beta, but we're going to be able to integrate this in closed form because we know the normalizing constant for a Gaussian. So that's where we're going to get this term to compute easily. These terms do get left in from the completing the square. They do get this is, and notice these are constant in beta. This is like the constant piece that we were ignoring. So if you do the completing the square that we did last time, and keep the constants in, you'll see these are the constants that are left. The constants left. And then these two pieces, this constant and this constant, I need to keep those in here. So notice I can go out. So those are still there. Okay. So that's the that's the form of everything so far. There should be a d beta, integrating over beta still, obviously. I'll just leave that off. Long story short, this thing doesn't depend on beta, so I also can pull that out of the integral. That stays around. If you simplify this thing, then you get an expression that is kind of large, but it looks like the following. Here, let me say, here our dimension, let's just call it D. So if we're doing the polynomial thing, this is the dimension of beta. Okay, so this is I plus 1 if we're doing the polynomial order I. But D is the dimension of beta.
So n is the number of
N is the number
points.
of observed data points still.
D is the dimension.
D is the dimension of beta, so the number of coefficients in my linear regression. Okay. And this is just the, actually I'm kind of writing this in a circle. This is just really the normalizing constant that I'm getting by integrating this normal distribution. I get this times the covariance matrix determinant. And because notice this is like the normalizing constant, not 1 over the normalizing constant. So this is, you have this 1 over this in your Gaussian, right? And that's what we get there. Okay. By the way, yeah, I should be careful. This term here, I'm being a little bit, is a Gaussian, the exponential part of the Gaussian, right, without the 1 over the normalizing constant. So I'm being a little bit fast and loose. Maybe I should have been more explicit there, but this is the e to the minus thing without the constant in there, because I'm going to integrate this and get the constant. That's the point. And this is that constant. So this integral of this is the normalizing constant for a Gaussian. That's the deal there. Anyway, I've still got, I left off the, I've got this lambda still there. 1.5. And then this term, you can actually rewrite, you could leave it this way, but you can also rewrite it in a slightly different way. This is actually equivalent to the following. This is the hard part to see algebraically. So if you want a fun algebra exercise, you can convince yourself of this last step. It's a little bit tricky. I mean, it's actually quite a bit tricky. It took me quite a while to get that to work, but I'm going to skip that for the sake of time because I want to cover a lot more stuff. So if you look at the code, the log of this is what I'm plotting. So this plot you see over here is if you took the log of all of this, that's what you evaluate. The log just makes the numbers a little bit more manageable to compute. It's taking exponentials of things. But notice this term now looks like y minus x beta squared. It's basically the sum squared residuals in your model. This term here, and then this is just your prior term. It's just the posterior mean times the prior lambda.
Now that first beta, should that be a beta n? Because we just integrated out.
Oh yes, thanks. Sorry. Yeah, thanks. Yeah, that would not make sense. Yeah, so this is the difference between your data and the max posterior model. Right, the regression curve, which is the maximum posterior, is represented by the beta n posterior mean, right, the Gaussian there. Okay, so these are just kind of like some normalizing constants that come in, and of course we're maximizing this over the space of models. If we don't change sigma squared, I can kind of leave off this constant because n doesn't change, my data sample size doesn't change, sigma squared isn't changing. I do have to keep the lambda because the lambda, as I change in our polynomial regression model, will change dimensions, and that's just a factor of the dimension there. I do have to keep this term in here because the d changes if I change the model. And then, of course, all the posterior things have to stay in there. So most of everything has to stay in there. But I could get rid of maybe this term if I'm just trying to compare relative values. That just scales everybody the same. Okay, but yeah, this is the evidence function. So this is the normalizing constant that you get from that completed squares exercise we did last time. And this is the thing that's telling you what is the probability of the data that I've observed under this class of models. And you want to kind of pick, sorry, yeah, I'm misspeaking, I always say this, it's actually not a probability, it's the likelihood, it's a density value of my data under this class of models, right? Okay, any questions about that?
Is it a proper probability?
No, so it's not a probability, yeah, so you have to be a little bit careful.
Because it does come out of Bayes' rule, right?
Actually, yeah, so if we, yeah, just a little bit careful. It's the, I mean, yeah, you really can't call it a probability. To be really careful, it's the density of y evaluated at my data. So it's just like when we do maximum likelihood. You have a likelihood function, which is the density function with a particular parameter, right? Now we, instead of having the particular parameter there, we integrate it over all the possible parameter values, but it's still like a more like a likelihood than it is a probability. It's not really a probability.
Is it because y is observed?
No, it's just because p of y as a function of y, and this is a function of y, is a density. It's a density function. So that's kind of, you have to be really careful. So yeah, so this is, see, if you think about it as like maximum likelihood, it's not the same as maximum likelihood. As maximum likelihood would say fix the value of beta and tell me the density value or the likelihood of y. Now we're saying just tell me the likelihood of y with no beta, just integrating out beta. And you can't do that without a prior on beta, right? Because if you don't have a prior on beta, then beta is not a random variable, and you wouldn't have a multiplication rule. If I just had, p of y given beta, then I'd have to actually set beta here. So I think this is a good connection to make. Maximum likelihood would say take just the likelihood, fix a particular value of beta, and that gives you a p of y, right? And then I want to find the value of beta that maximizes this likelihood. In the Bayesian case, we can just get p of y by this. What we're doing here, if I kind of simplify the notation, is that I'm integrating this thing over beta. So this would be like your maximum likelihood, where you kind of think of beta as constant, and you maximize over the possible values of beta, but you still have a likelihood. But this is a density. It's not a probability unless I integrate over some range of y's. Then it's a probability, right? I'm actually evaluating this density at my data. Here, again, I'm evaluating this density function at my data, but because I have a prior, I can actually integrate out, make this not depend on a particular choice of beta, and just say that this is really dependent only on kind of the whole class of models I'm choosing. So what I'm trying to do is I'm trying to decide which class of models would be the best class of models to use for this data set out of a certain discrete set of choices of models. So that's kind of the idea. So it's related to maximum likelihood. It's analogous. You can kind of think of it in that way. Any other questions? Okay. So yeah, so that's the end of the derivation I was going to do. And again, I left off the really hard step is getting from here to here, and I would recommend it as a exercise if you want to try some fun algebra there. Okay. But yeah, what I'm going to do now is switch back to. I've actually got slide presentation for today's lecture. And what I wanted to talk about today was this is a presentation I gave a tutorial I've given a couple of times at conferences, and so I realized that I could just it's some of the stuff I want to cover today, and so I just kind of adapted it for our class today. So anyway, that's why it's slides. I don't usually do this, but anyway, yeah. So we're going to talk more about model selection today. So what we see with the evidence function is that if I have a bunch of different types of models, I can compute the evidence and pick the one with max evidence. And I mentioned kind of the last time, this works nicely for polynomials because we can do this in a nested fashion. So I can start with a zeroth order model, just a mean. I can add a linear component to get a line. I can add a quadratic component to get a parabola. And anyway, I can keep adding a new coefficient each time, and it includes the previous model, and it just adds to it. And then that gives me just maybe k, models that are all subsets of each other, and I can do that plot that we did with the log evidence. But the general model selection problem could be I've got a choice of tens or hundreds of variables, and any combination of those variables would be a valid model. Okay? So if I have an X matrix with a certain number of columns, the question is, which columns would I want to actually keep in the X matrix, and other columns I would possibly maybe throw out. And then it becomes a combinatorial problem. So it's all possible subsets of variables, right? So it's 2 to the k kind of options. And so computing this evidence function, although it's closed form and it's nice and quick, if you have to do it an exponential number of times, that gets unwieldy when you get too many variables. And so we're going to talk about an approach based on, and probably most of you have run across this at some point, especially if you took machine learning, based on sparsity. And we're going to talk about a couple of different ways to do model selection. And the other thing we're going to talk about is what's called an information criteria. Okay, so let's okay, I'm not sure why I was to do that. Okay, so I swear I do this all the time and this doesn't show up. I don't know why it's doing this. Okay, I'll just move ahead with this. Oh, maybe I can do it. Okay, there we go. Okay, great. Okay, so yeah, so model selection. Okay, so we've already seen this is our model. Just to remind you. And so now the general question, as I mentioned, is if I've got a choice of k variables, and you can imagine, we'll see an example here in a minute, but you can imagine like you've got a data set with just a ton of different types of data in it. And which of those data points do I want to include that are predictors of y? So some of these data types might not have any relationship to y, and they just make my model more complicated for no good reason. And the question is which ones to include in my model, which to not include in my model. And so this is the data set you've already seen in the last homework, is the brain data where we have hippocampus volumes, right? And we didn't use most of the variables from that data set, but now what we're going to do here is take a look at what if we use a few more of the data points. In the homework assignment, you just used basically used the clinical dementia rating to just cluster people into control subjects, mild dementia, and then full-out dementia groups, and compare the 3 groups. But we have a lot more information about subjects. We also know their sex, are they male, female? We know their age, so you can think that kind of as a continuous variable. And we know another test is the mini mental state exam, is kind of a memory test. We know the intracranial volume, so that's how much space is in their skull, basically. And then the whole brain volume, that is the volume that's brain that's inside the skull, which is not always the same as the amount of space in your skull. And so anyway, we've got a few other variables, okay? And so the question is, we've got 1, 2, 3, 4, 5, 6 variables. There's actually a lot more variables we could throw in here, but let's just, for the purpose of this example, say we've got 6 variables, and we want to know how those variables relate or predict the hippocampal volume. And we'll stick to just like right hippocampal volume. We could do right or left. Now, if I just wanted to look at all possible combinations I could get from 6 variables, I've got to look at 2 to the 6 possible subsets, so 64. It's not a big deal. We can actually do it. We're actually going to do that. We're going to look at all possible subsets and find the best one. We can do that for this, but you can imagine if I start to get to 10, 20, 30 variables, I'm already starting to get unwieldy, and usually we have really higher dimensional data sets we have to deal with. Okay, so but that's, and this isn't the whole table, by the way. The head command just gives me the top of it so I can show the screen. I can't remember, there's a lot of subjects here. Okay, so as a modeler, as a data analyst, I first have to take the question I want to answer and then turn that into a model. In my own research as a data analyzing data, I typically am getting my hypotheses from a collaborator, in this case, like a neurologist studying Alzheimer's disease. And so, for instance, we might have a hypothesis, or the kind of neurologist studying this data set might have a hypothesis that the hippocampal volume decreases with age. Okay, so as we get older, our hippocampal volumes shrink. That's a hypothesis. It's thought to be a true hypothesis, by the way. Another hypothesis we might want to ask is, or study, is lower hippocampal volume is associated with cognitive decline. And by cognitive decline, we mean people with dementia. And we've actually got 2 measures of dementia. The one you already looked at was the CDR, and then the MMSE are actually 2 different measures of dementia. And so these are some hypotheses we might want to study or kind of look at in this model. Now, the problem is that, if I just say, okay, if I want to know, does hippocampal volume decrease with age? Well, that's easy. I just do linear regression of hippocampal volume versus age as my x variable, and I'm done, right? And the problem with that, we're going to see, is that it's not that simple when I have other variables that might explain the hippocampal volume, okay? One possibility is I just include all the variables, and you might ask, why not just include all the variables? And again, it's kind of similar to, we go back to the polynomial regression. If I just keep including lots and lots of coefficients, I can overfit my data and actually not get the meaningful result that I want about the coefficients I'm concerned about. That result, we'll see in a minute, might get washed out or changed depending on how I include other variables. So which of these covariates, like intracranial volume, white brain, whole brain volume, age, age is of interest. Should I include male, female in there, for instance? So anyway, that's kind of the dilemma that you have as the data analyst presented with this type of data set, or really basically any kind of data set. You have this modeling dilemma. Okay, so I'd like to again bring up our mantra of the course, and this is really apt for model selection, is that I find it a comforting quote in the sense that no matter what I do, I can't. All the models I could choose from, they're always going to be wrong. So I at least have that guarantee. But the goal here, as a person modeling this data set, is that I need to find a model that is useful. And actually, more importantly, is that some models are dangerously misleading, and that's what we really are trying to avoid. So we're really trying to avoid models that are going to give us incorrect conclusions from the data. And we'll see how to try to prevent that. So first thing we could ask is, why not just include all the variables? Let's include all 6 variables, right? And I think I already made these points. You have this danger of overfitting, and the related problem is that if you try to estimate lots and lots of parameters, to do that robustly, you need lots and lots of data. And the more parameters you add, the more data you're going to need. And we typically, unless yeah, be careful with so-called big data. I guess you can solve all problems and never have to worry about overfitting, but almost always is the case that you don't have enough data to just pile on parameters. The next thing you might consider doing, if you remember from your just basic statistics, you get frequentist statistics, you do a hypothesis test on a linear regression model, and you get a p-value, right? And you can get a p-value for every coefficient in the linear regression model, and then you might just say, well, why don't I just include variables and keep the ones that have a significance. Let's say I set my significance level, my alpha level to the usual magic number, 0.05, and every p-value below 0.5, I'll call that significant, and I'll keep that variable. Every p-value above 0.05, that's not statistically significant, again, this arbitrary threshold, and I'll say, I'll throw that variable out of the model, okay? And this is actually not far off from what some people do, and we'll see in a minute, this is actually quite dangerous to do. So what happens if I do that? So here in R, I can start off with just the age effect. So this is just y equals x plus noise, is kind of the notation. There's a tilde here, that's the notation from R. But this is basically saying my y variable is the hippocampal volume. I have one x variable, and that's the age. And it always adds an intercept unless you tell it not to. So there's also an intercept here, of course. And so the thing you get if you do the kind of the hypothesis test on this, if you're not familiar or used to seeing these tables in R, I'll just really quickly say, the first thing it gives you, the first column it gives you is the estimate, so that's the intercept. This is the slope, so this is the coefficient, the beta coefficient for age is the slope versus age. And then it gives you the standard error, which is just the sum squared residuals, square root of that divided by n. And then it gives you the t-statistic associated with the hypothesis test for that, because we're assuming Gaussian and all that kind of stuff. And then it gives you a p-value for that hypothesis test. And so we don't care about the intercept. That's just that's not really meaningful, so we're going to ignore that. But the age we see is 10 to the minus 9, so way below our magic threshold of 5%. And so we're going to keep age in there. We say, okay, that's a significant effect. I like that. I'm going to conclude that yes, the negative slope tells me as we get older, our hippocampal volume decreases, and that's a significant effect. So we're kind of happy with this result, and we think let's go publish a paper about this result that we found. And here's if you plot it. The data set goes from 60 to 95 in age, and we see that it does seem to make sense that there's a negative trend in hippocampal volume with age. And so the significant level makes sense there. Okay, but now let's say we want to add some more covariates here. And so the next covariate we add would be possibly maybe male-female. Okay, so this is age plus m.f means m.f is just this kind of binary variable that's made male-female, and this is in age. And then, so now I have two coefficients plus a third coefficient for intercept. So beta 0, beta 1, beta 2. And again, I do the linear model, and I get p-values, and again, I get that these are both significant effects. And so that tells me that the sex variable is also helping to predict hippocampal volume. And so I'll keep that variable in there. So it's 10 to the minus 2, so it's 0.009, and I might keep that in. Actually, wait a minute, 10 is 0.09, right? Okay, so Isn't it 0.0? It's 0.09, right? Yeah, so actually, I made a mistake here. Or maybe, yeah, anyway, sorry, I made a mistake here. Yeah, so, or maybe I was thinking of a 10% magic number. Anyway, so here, okay, sorry. So here you might decide to remove a sex, depending on what your magic threshold is. If it's 5%, you would remove it here, because this is 9% p-value. So I got that backwards there. So yeah, so we might remove that. Now let's throw in whole grain volume. Now all of a sudden something very interesting happens. I throw in whole grain volume, and now I do have this the right way. If I throw these three in together, male-female is now significant. It's suddenly 0.00, now it is 003, so that is below 5, 0.05. And whole grain volume is significant, it's 10 minus 9. But our age, which was hugely significant before, which is not a real thing, but hugely significant, was 10 to the minus 9. Now it's only 10 to the minus 2, and it's just above the 5% threshold, just slightly above. It's popped over the threshold, and we're going to now decide to remove it and say there's no age effect because it's not significant. So very strange things happen if you just say I'm going to use different combinations of variables. Depending on which variables you throw in there, you'll have variables pop into significance and pop out of significance. And we just saw age popped out and sex popped in, if you will, into the significance, into our. So if you try to choose things based on their p-values, their significance level, it's chaos. And this is actually a strategy people use. There's even procedures that you can find if you look up online. People will recommend try to include variables and one at a time. And every time you test a variable, you see is it significant. And if it is, you keep it in there. And you can see that's really dangerous because you then have to go back and revisit variables that start becoming insignificant all of a sudden, and it becomes a mess. So this is not a great strategy. So I'm going to do one more. So now we're including the CDR dimension rating, and now boom, everything's back to being below the 5% magic level. So yeah, so it's a little bit crazy.
What does it mean that your intercept is not significant?
Oh yeah, now the intercept's not significant. Typically, we don't ever test like dual hypothesis test significant. It just always, R always prints out that row, but we typically don't actually care, because this is basically what is your hippocampal volume at age 0, right? That's what the intercept means. And that it makes no sense. Because first of all, between our plot is only between 60 to 85, right? And so we can't really trust this line where we don't have data. So the intercept is, you should not look at it, basically. It's basically needed because you need to specify this line, but doing a statistical test on it would be a mistake. You could recenter your data so that, say you did want to know the level at age 80 or something, you would recenter your data to 80 so that 0 became 80, the age. Then you could, if you wanted to know, is my hippocampus significantly different from some value at age 80, you could do a statistical test of it. But for the purposes of this, we're just kind of ignoring, for the statistical testing, we're going to ignore the intercept. Okay, so yeah, so we've got this crazy changes that there's no really obvious way to pick variables based on their p-values and their significance levels. So that's the conclusion, basically. The other conclusion is that if you are evil, you can manipulate your results, write a paper, publish some result, or put out a press release saying that something's correlated to something, or that something causes Alzheimer's disease by just kind of manipulating covariates. So you can take this data set and maybe throw in the person's eye color or something, and maybe
manipulate your variables in just the right way that you can get, like, people with green eyes get Alzheimer's disease. So anyway, which I don't think is true necessarily. So you can be very dangerous with model selection, and that's kind of the point. And so how do we prevent doing dangerous things and having misleading models? Really the only way to do it is through having a procedure which is going to automatically choose your model for you without you overly kind of tinkering with what goes into the model. So some automatic method for choosing amongst a class of a set of models. And we've already taken a look at one possible strategy, which is to compute in the Bayesian regression case, to compute the Bayesian evidence. And the idea is that you have to kind of fix this procedure, this automatic method, before you set out on your quest to analyze the data. So you have to decide, I'm going to choose models this way, and whichever model this automatic method chooses for me, I'm going to go with that model and use that result. Because if you then say, you could get into a similar dangerous situation if you say, well, maybe I'll use Bayesian evidence, or maybe I'll use sparsity, or maybe I'll use these information criteria we're going to talk about, and then you would just pick the automatic method until it gave you the answer you were looking for. It's kind of the same fishing expedition. So the idea is that, to do let's say sound statistical analysis, you need to have a decision rule for how you're going to choose your model. It should be automatic and not kind of just decided on by you, the analyst, and you have to kind of stick to that one strategy that you choose from the beginning. Yeah, that's kind of what I'm saying. Okay, so here's another possibility. What if I said, and this we kind of already talked about, what if I just have I've got a linear regression, I've got, yeah, question?
I'm a bit confused between feature selection and model selection.
It's equivalent. What we're talking about is exactly feature selection. So in the linear model, and I'm sticking to linear models, but you can imagine any old machine learning algorithm in any old model, the x's, x1 through xk, are my k features. And what I'm doing here is I'm doing feature selection. So I'm glad you brought up that word, because this is exactly what we're talking about. Yeah.
Once you choose a set of features as valid features, then depending on hyperparameters for each combination of, each feature set that I choose, I can get several models based on what hyperparameters I choose to generate these models. So after making this choice of these are relevant features,
Yeah.
you still have another step of.
Yeah, that's right. So, okay, so yeah, let's back up a little bit. So when I'm talking about model selection in terms of so I'm talking about model selection in the sense of, I'm really sticking to linear models, and it's really feature selection. I really should call this feature selection within linear models is the example we're doing. But the principles are more general. So what if I had a linear model and then a nonlinear model, like something that was like an exponential growth model, or something that where the coefficients were inside a nonlinear function? I could still do model selection between the linear model and the nonlinear model. So there's kind of two. You can kind of break it into two things. Like I have models that are completely different classes, like a linear regression, a nonlinear regression, maybe a non-parametric regression, Gaussian process regression that we'll talk about later in the semester. Lots of different models that aren't the same type of model at all, and that's really kind of choosing between really disparate models. But then within a class like this, where I've got a choice of which features to include in that model, so how complex to make this model based on feature sets, and I can take any feature set and make it even more complicated, like we see with just starting to include x2 squared and x2 cubed or xk squared, or even multiplying x1 times x2. This is where you get into like kernelized methods, or basically creating new features from your original features. And so you can make a linear model like this even more complicated with kernels, and then I'd have to choose what kernel features to use. So these are kind of like generated features. So yeah, so this includes all of that. Yeah, so feature selection from your raw data, which feature, so if I don't even call these features, I call these like covariates in a statistical analysis. Which covariates do I include? I could also use these ideas to which features do I generate, new features like polynomial features, for instance. And I can also use it to compare models that are just completely seem to be apples and oranges, like completely nonlinear model with a linear model. So yeah, so all of that is kind of subsumed. I'm kind of putting it under the umbrella of model selection in general. But that's a good distinction to make, because there's lots of different moving parts there. You can consider all those things. And yeah, the idea is you kind of have to, kind of settle on, you can't choose every model under the sun. You can't look at every model under the sun. You have to kind of narrow as the person analyzing the data, you have to come up with, these are the plausible models that could explain this data. And then kind of stick to those, and these would be plausible variables that I should put into the model, the features, or rather, I should put into the model, and kind of make all these decisions as the modeler first, and then let kind of this automatic model selection take over from there is kind of a, if you want to be careful about it. Now, this isn't to say I should be a little bit careful, I would be a little bit contradictory to myself here, that as you're modeling things, you might find you go through this whole analysis and you get just like a model that doesn't fit the data at the end. Like it doesn't explain the data very well. You then do want to go back and reevaluate, go back to the whiteboard and think about, okay, I need to do something that's going to really explain this data better. So you might visualize the data or do some heuristics, and maybe see a plot of it at some point and say, that model is really not looking like it explains this data. And then it is okay to go back and reevaluate which models you're using and maybe try something different, but you want to be careful that you're not, the idea is not to do this like p-value fishing, where you're specifically trying to answer and say, yes, I want this to tell me that age is that my hippocampus is decreasing with age. I want it to tell me that, and you just fish and fish and fish for a model that tells you that. That's where it gets dangerous. Okay. So another potential strategy, which doesn't work, is to use just the likelihood itself. So if you remember from regression, we get an R² value. Remember, that's the percentage of variance that you're explaining in the regression model. So if all my data lies on a line, and I fit a line to it perfectly, then 0% of the variance is left over. I've explained all of the variance in the data by that line. So the error in the model that's left over is 1 minus that. I get the R², basically. So a value of 1 for R² is perfect. Your model fits your data perfectly, and there's no error left over. I should say no residuals left over. And so anyway, I could just plot the R² of my regression model versus the particular model I'm going to pick. And the problem with that is that you'll always pick more complex models. So if I add a variable in a linear regression model, it can only increase my R², which is a proportion. It's also the same thing as the likelihood. The likelihood can only goes up when I add. So just to write down the Gaussian likelihood, if I add another variable to an existing model, it's going to always increase the likelihood. Or at best, or at worst, I should say, it's going to stay flat if that didn't change anything, but it can't go down. So you're only going to select more complicated models by this strategy. So that doesn't help at all. The idea is, and this is again a kind of theme in kind of Bayesian regression that we talked about, how we want to shrink the coefficients to zero, is the same kind of principle. Is Occam's razor, we want to use the simplest model that still explains our data. So if you get too simple, it won't explain your data. But we want to be as simple as we can possibly get and still be able to explain the data. And in this case, in our example, with the linear regression, simple means few parameters. So we want as few parameters as possible to explain the data. That's kind of the principle. And so these information criteria are one way to go about that. So this is the Akaike information criteria, or AIC. And actually, what's funny is that Akaike did name this the AIC, but he didn't name it after himself. He was calling it an information criteria, so that was the AIC, and everyone else has been calling it Akaike information criteria since. So anyway, he wasn't arrogant enough to name it after himself, but anyway. So there's this AIC, and it looks like this. So K is the number of parameters in our model, is the D we were doing over here. So K is or I guess in these slides we've got K are the number of variables we're including in the linear regression model. And then the 2 log L is just the log likelihood, 2 times the log likelihood. So just the log Gaussian likelihood, it's basically the sum squared error, as we see in the sum course. And so that is the AIC. And we want to maximize this information criteria. So what we want to do, we want to minimize this. So what we want to do is, this has a negative on it. So we want to maximize the log likelihood, but at the same time we want to minimize the number of parameters. So we want K to be as small as possible and log likelihood to be as big as possible. And they compete with each other. If I increase K, it's going to make this bigger, but it's also going to bring down the likelihood sum, bring up the likelihood, which makes that negative term go down. So they're going to kind of compete with each other. More complex models are favored by the log likelihood term, and simpler models are favored by the K term. And when they balance out, that's the model that we pick based on the AIC. So it may seem like, well, this is a very simple, like I just have K, and it's trying to fight out with log likelihood, and I'm just adding them together. They both have a factor of 2, so I'm just kind of adding together. That seems like a kind of a hokey way to do this. Yeah, question?
Isn't it same like sparse coding or something, where you use a norm and number of elements?
You were like 3 slides ahead of me. You're right. It is exactly that. Yeah, we're going to see. This is exactly equivalent to sparsity. So you have ruined my punchline. That's fine. No, very good insight. Yeah, no, that's great insight. This is exactly it's exactly equivalent to sparsity. We'll see in a second. Yep. But the AIC, even though it looks like just weight the number of parameters with the log likelihood equally, it turns out to be there's a derivation for why to do this. Yeah, question.
It's not log likelihood, it's just log likelihood.
Log what?
You have the
Capital L is not
Yeah.
log likelihood.
Oh, yeah. Oh, yeah, right. That's not the log likelihood. It's just the log, yeah. Log of capital L is the log likelihood. So that L is the likelihood. Yeah, thanks. That's important. Wow. I've given this talk with this slide at least a couple of times. You're the first one to notice that. Okay.
We've been building all around models.
Okay. Right. So in the Gaussian case, our log likelihood, and not a log likelihood, but just log likelihood, is the log of the average squared residual. So epsilon I is just that this term, y minus x beta kind of term. Okay. Where beta now, I should be careful. This isn't just a likelihood model, by the way. This is the model we've been dealing with so far. It's just likelihood. There's no Bayesian, so there's no prior on beta in this Akaike information criteria thing. This is the log likelihood, Gaussian likelihood. So we're going to use the beta with the max likelihood to get these max likelihood beta to get these residuals. Okay, so that's the exact equation to compute the AIC for a Gaussian assumption in your Okay, so this is going to be, again, not a complete derivation of the AIC. If you want a complete derivation, I think I have a, this paper, this review article, will take you through all the careful derivation of it. So if you want to look at that in more detail, you can find it. But this is the basic, I'll just give you the gist of the derivation here. So what we're doing when we are doing AIC is that our data is coming from some unknown density f of x. So assume x is a random variable that our data is coming from. I guess I should have called this y. It's really the y in the linear regression case. But anyway, this is the data, the random variable we're interested in. We don't know this true density f of x. What we have are a bunch of models which are really probability densities. So this is like our m sub i's. And they're basically, the m sub i's are probability densities of our x, random variable, and they have some parameters theta I. So we have some parameterized kind of densities or classes that are trying to represent some unknown f of x. And so what we're going to do is we're going to try to minimize what's called the Kullback-Leibler divergence. And I think, have people seen KL divergence? Okay, so no one's seen it. Okay, or no one will admit they've seen it. It's okay to admit it if you've seen it. Okay? So the KL divergence. This is going to come up in class again. We're going to talk about it in more depth. But for the time being, I'll kind of skim over it for the purposes of the AIC discussion, just so I can get to the end of the slides here, hopefully. Basically, what it's doing is KL divergence is a divergence between f and g. So it's saying how similar f and g as densities. If f and g are exactly the same, if their area is exactly the same everywhere, then this will be 0. If there's differences in kind of where their mass is located, this will start to get larger. So you want to kind of minimize KL divergence to get these two densities as close as possible. By the way, it looks a lot like, this is like entropy, right? This is p log p integral. This is negative entropy of f, and this is what is called relative entropy. If you think this is relative entropy, is f and g, the entropy of the kind of the two of them there together. So anyway, obviously you can see if f is equal to g, this is 0, right? So that's easy to see. But it's a little bit harder to see that this is positive. It's actually not symmetric. So if I flipped f and g, I could get a different answer. So it's not a distance. So you have to be careful not to call it a distance. It's a divergence. But it's not a distance because it's not symmetric. If I flip the two probability distributions, I get possibly a different answer. Okay, so the point is we want to minimize this KL divergence, which somehow tells us how close f and g are. But I can't compute this, right? Because I don't know f. F is the true density, and I don't know it. That's the whole point. If I knew f, I wouldn't need to be modeling things. So the really cool trick that Akayaki realized was that you can't compute this KL divergence, but you can approximate it, and the approximation is only off by a constant in GI. So constant in GI means that it doesn't depend on GI. And so your approximation of the KL divergence, you can compare the different G's to each other because you're only off by a constant. So the relative difference between the KL divergences is the same as the true KL divergence. So yeah, so that's the trick in the AIC. Is that's what you're doing, and again, I won't go through the hairy details of how you set up the approximations to show that it's only off by a constant. But that's the nature of it. Yeah, this I won't mention too much. You can correct there's a bias in the AIC. It's biased, which doesn't make too much of a difference unless you have a fairly small n, like very small sample size. If you have a small sample size, you can do a second order correction of the bias But anyway, that's a bias corrected AIC. And yeah, if you want to know more about all this stuff, read this paper. It's a good one. You can also read Akaigi's original paper, but this one's a little bit more digestible probably. Okay, so one strategy is if you don't have that many models, or that many variables, I should say, if you only have k variables, 2 to the k is not too bad. And AIC is really easy to compute. It's just 2k minus the sum squared residuals, kind of, or plus the sum squared residuals kind of thing. And you can flip through all your models if you only have, if 2 to the k is only like in the thousands or so, you're probably good to go. And this package, FindMinIC, will do exactly that. It's actually a package that my research group wrote, and it's on CBRAN. And you can go through all possible models. Don't do this if k is like 100, your computer will freeze. But if your k is like 10, 15 or so, it's probably fine. And what it's going to do is pick the absolute best AIC that you can get with any possible combination of variables. So for our hippocampus data, this is totally possible. It's only 6 variables. So I put in the full model with all 6 variables included, and I put it into this FindMinIC function, and FindMinIC will return a ranking of the models based on their AIC. And so the top one, I've just listed the first 5, but the top one is the best model it found, and only by 1. So the AIC is 2814, and versus the next one is 2815. So this one says your best model includes age, clinical dementia rating, intracranial volume, and whole brain volume is kind of your best model. One thing you do have to be careful about is if you have 2 competing models that have very, very similar AIC, choosing the best one is, not necessarily a foolproof strategy either, right? So, I mean, like, this is saying that I've actually got these first 4 models are fairly similar, but with no other thing to go on, you might as well choose just the best one that you get here. And then I can take that best model and now call my linear model on it and get what is significant. And in the end here, this would be maybe the analysis I go with AIC is the thing I've chosen to pick the best model. And this tells me that age, CDR, and the 2 volume measures are all, magic number, below magic number of 0.05. Okay. And now the connection to sparsity. So it turns out that, let's talk about sparsity, then we'll see that its connection to AIC. So another strategy, which, as we've heard, turns out to be equivalent to AIC, is to choose your variables based on a sparsity criteria. And so a sparsity criteria is basically another version of a penalized likelihood, or penalized log likelihood. So we talked about how this Bayesian regression, you can think of this beta lambda beta thing being a penalty on the beta coefficient, shrinking them to 0, and we're just penalizing the likelihood, the usual Gaussian likelihood. Well, another way to penalize your Gaussian likelihood here, this is basically our log likelihood without the constants. I can just put a penalty on it, which is the 0 norm instead of the 2 norm. I've got the squared 2 norm here. And the 0 norm basically just counts how many elements of beta are non-zero. Okay, so this will be some number between 0 and k. I've got k total coefficients. And the number of beta elements that come out to be something other than 0 will incur a penalty of 1 in this norm, and then scale by some factor of lambda, which is the gradient. Okay, so that term wants to reduce the number of coefficients. And optimizing this, I think you can see already that this is equivalent if I just set this lambda to a 1. This is essentially equivalent to the AIC. In fact, let me just skip to that real quickly. So yeah, so, or no, yeah, the log likely has a 1/2 in it, that gets canceled. So yeah, so say lambda to 2, I get this turns out to be the same thing as AIC. So your direct sparsity thing is actually the same problem as solving the AIC. So let me, that's, I'll back up here. Now, people don't do this though. They don't do the AIC exhaustive because of this. It's NP hard, in K, as we said, right? If I start to get a lot of variables, if I had more than the 6 variables here, I had like 20 variables, I might start to think 2 to the 20 or 2 to the 30, whatever. It's going to start to get too large eventually, and I can't look at every possible thing. And there's no polynomial time algorithm to compute this. So exhaustive search is the dumb way to do it, maybe, but it's not like there's a smart way to do it in polynomial time in K, because it's actually NP hard. There's not much better choice than kind of enumerating and going through these things. Okay, so what do people do? They actually take what's called the convex relaxation of the L0 norm. And the convex relaxation of the L0 norm is what's called the L1 norm. And the L1 norm is just a sum of the absolute value of the components of your data vector. So instead of counting the number of non-zero elements, I'm going to replace that with the sum of the absolute values of the elements of beta. And now this is called the lasso, by the way, and it's very famous. This kind of is one of the things that really got this idea of sparsity, sparked this made it really popular because people showed that you can make this. And what do we mean by convex relaxation, by the way? What we mean is you're taking this very non-convex thing, which is this like threshold, like it's either 0 or it's 1, and then I'm making it a convex function. So the absolute value is a convex function, and convex functions are much easier to optimize. And so, we're now adding together 2 convex functions. I get a convex function optimization problem, and I can do this computationally efficiently. And so this kind of makes sparsity a manageable deal. And so this paper by Titchrani and others in '96 kind of introduced this lasso concept. Another possibility, and this becomes now more of a Bayesian strategy, but to do sparsity. So notice the ridge regression shrinks things to 0, but it doesn't make things sparse. So sparse means I want to penalize things that are just anything other than 0. And this will shrink things to 0, but it doesn't care if it's really close to 0 or exactly 0. So it's not going to make things exactly 0 necessarily. So if you want things to be selected or deselected, you need them to go all the way to 0. That's the idea with sparsity. So now a Bayesian type approach to doing sparsity is this paper by Figueiredo showed that we can do sparsity adaptively. One of the problems with the sparsity here for the L1 penalty is you have to pick this lambda. So there's no longer, with L0 penalty, we could pick lambda equals to 2, and it was exactly AIC and what we wanted possibly. But this doesn't anymore relate directly to AIC, so there's no obvious choice for lambda. There are ways to choose lambda, but you typically would do something like we talked about, like a cross-validation or something like that to get a lambda that makes sense for your data. So what Figueiredo did was something called adaptive sparsity. There's lots of different sparsity things. I'm only touching a couple of things here, by the way. So I'm giving you the kind of original formulation, then the lasso is the first kind of convex one, and then there's a bajillion things between that and this is just another one I have that I actually kind of like myself. So anyway, what we do in adaptive sparsity, what Figueroa does is he takes the beta, your coefficient, and gives it a Gaussian prior, just like we're doing here. So it has a Gaussian prior. But then the tau, which is the same thing we're calling the little lambda times identity, he then gives it a prior, and that prior is Jeffrey's prior. So it's 1 over tau. And so there's no parameter here. Because tau is a random variable, you can actually integrate tau out of the equation, and you're left with no lambda parameter that you have to set. Because, again, we're doing a non-informative hyperprior here, and the hyperprior has no parameter. So that's the idea is that I still want to get maybe a mapped estimation, maximum posterior for beta, but to do that, I'm going to marginalize tau out of the equation so there's never a parameter to deal with. And it turns out that if you do that, it's equivalent to putting your log prior looking like a log absolute value of beta. But numerically, you have to add the split factor. If you wanted to do that directly, I should say. If you see the details in this Figueroa paper, you don't actually put in a fudge factor. But if you wanted to say, like the lasso, say I've got a likelihood plus a penalty, that penalty would look something like this. And it just looks like a log penalty. And I'll show you why this makes a lot of sense in the next plot here. If you look at the L0 prior, which is what we kind of want, that's like true sparsity. It looks like everything gets a penalty of 1 unless it's a 0, and then I suddenly jump down to 0 penalty, right? The L1 is absolute value, that's my penalty. If you do the adaptive sparsity kind of Bayesian with Jeffrey's hyperprior, you get this log type function which looks like that. If we kept going further, that blue curve would obviously it's log, it would go over 1, but that's kind of the penalty that you're creating there. And you can see the blue, the reason it's a little bit nicer is that it gets us a little bit closer to this true penalty that we want. And I should mention there's just a ton of other people that have done things that are similar that give you penalties that get you closer to what you want, yada, yada, yada. Yeah, we also have a package that we've contributed called Adaptive Sparsity. It does exactly this. It also does some research that we did, but that's not what I'm going to talk about. Just really quickly, I'm out of time, but if I could just have 1 more minute. If you do this adaptive sparsity for this linear model, it chooses the same age, CDR, whole brain volume, and intracranial volume, and sets the other things to 0. So it's the exact same selection that AIC gave us. So, and it makes sense because we're getting a lot closer to what AIC is equivalent to. And then the last thing I want to mention is if you go through these notes, I've got the polynomial example, but just done with, that was what we did with ridge regression, and this is the adaptive sparsity regression. So it gives us, again, a simplified, but notice the way it does it is it zeroed out everything except for this one, like, I don't know, 5th order coefficient. And so it doesn't give us back the true beta we wanted, but it does actually give us a very reasonable looking curve by simplifying. And it's actually a problem with polynomials is that a 3rd order polynomial looks a lot like a 5th order polynomial. And so it's actually not easy if you use sparsity to choose that this was exactly a 3rd order polynomial. But that's probably okay if your goal is to fit your data and keep the curve fairly simple. This is only using 1 coefficient, just a 5th order coefficient, and the actual shape of the curve looks nice and simple. So this is probably a decent solution if that's what you're after. Okay, so that's everything I have. Thanks.